In this lesson, we'll take a look at equivalent forms of exponential equations, and in the first example, you were writing everything as powers with the same base. And we'll use this idea of equivalent forms to solve a couple of exponential equations in example 2. So first of all, in example 1, it's express everything as a power with a base of 2. And when we start here, a, the 4 squared, is a power with a base of 4. So we want to change it so the power doesn't have a base of 4, it has a base of 2. And so I think of, well, what can I write the 4 at? How do I write that as a power with a base of 2? And of course, 4 is equal to 2 squared. So I'm changing this 4 into 2 squared, what's in the parentheses here. This power of 2 here is that power of 2, not this one in here. So that square is that square there. Now when you have a power of another power, you multiply the exponents. 2 squared squared, we multiply the 2 exponents, and so that equals 2 to the power of 4. So I've kind of converted. I still have a power here, but I want to write everything as a power of base 2. That's what the question asked. So 4 squared is equal to 2 to the 4th. That's a power with a base of 2. In example B, I want to find what power of 2 gives me 64. And I could go 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. I'm up to 5 2's now. And times another 2 makes 64. So 2 times 2 times 2 times 2 times 2 times another 2 is 2 gives me 64. So 64 is 2 to the power of 6. In C, I want to write all this as a single power of 2. And so I'll start by writing the 8 and the 128 as powers of 2. Now 8 is 2 cubed. 2 times 2 times 2. 3 2's multiplied together gives me 8. So that's why 8 is 2 cubed. When you have a cube root and then you're squaring, that's the same as writing to the power of 2/3. Notice the power here. The 2 that this is raised to is the numerator, and the root is the denominator in that rational exponent. Now 128 is 2 to the 7th. Remember back in B, 64 is 2 to the 6th. So we multiply by one more 2, that would be 128. So we'd have 2 to the 7th. So 128 is this 2 to the 7th here. And again, the 7th root and then cubed would be the power of 3/7. Again, the exponent here is the 3 in the numerator, and the root is the denominator. Now when I multiply 3 by 2/3, again power over power, so I'm multiplying the exponents, notice that these 3's will divide out. So they divide, I'm left with 2 squared, and then these 7's will as well. 7 times 3 7's, the 7's divide, and I'm just left with 3. I could also think of 7 times 3 is 21 over 7. Remember, it's still just 7 in the denominator, because the denominator of this 7 is 1, and that 1 times this 7 would still be 7. But if I multiply that to get 21 sevenths, that's still 3, because 21 divided by 7 is still 3. So I'm multiplying two powers with the same base. I just add the exponent, so 2 to the squared times 2 cubed would be 2 to the 5th. So I've written all these as powers of 2. Now notice in D, D isn't a whole number power of 2. It's not 2 cubed, 2 to the 4th, 2 to the 5th, or 2 to the 6th. It's not a whole number or an integer power of 2. And so what we're going to do is we're going to say the 20 is equal to 2 to the power of x, and we have to find what x is. And the way I'm going to do that, I'm going to use logarithms. I'm going to rewrite this in its equivalent logarithmic form. And the logarithmic form solves for x, the exponent. And so x equals the logarithm of 20 base 2. Remember, when you convert to logarithmic form, the base of the power is the same as the base of the logarithm. Bases stay the same. And so that's the exponent. And so I would write then my 20 as, and I'm substituting this in place of x here. Okay, logarithm base 2 of 20. So 20 is 2 to the power of the logarithm base 2 of 20. Notice that in this power with the logarithm and the exponent, the base of the power and the base of the logarithm are the same. And notice if they're the same, then what this is equal to is this number here. This 20 is not by coincidence just the same as this 20. That would always be the same. And we could actually generalize that to a rule. And the rule would look like this. If I had, let's say the base, I'll call it a, to the power of the logarithm, and so the base of my logarithm has to be the same as the power, so it's a base a as well, of, let's say we'll call it x. As long as this base and this base are the same, then that would always equal the value x. Now, A way we could also verify this particular one, we could actually use the graphing calculator and evaluate 2 to the power of, and remember the logarithm base 20, base 2 of 20 in your scientific calculator would be the logarithm of 20 divided by the logarithm of that base 2, and it does work out to 20 exactly. Okay, so that's just a verification that this actually is true. This is the rule in general, however. Now in example 2, we're asked to solve by changing the base. So we want to write both powers with the same base. So we look at the base 2 and the base 4 and think of what common base could I write both numbers as powers of. And so 2 is the simplest base. This already has base 2. And of course 4 is just 2 squared, like we changed this 4 into 2 squared here. So I change this 4 into 2 squared. I still have the exponent of x plus 1 here. And I haven't changed anything on the right side. It's still 2 to the x minus 1. Now remember, power of a power, you multiply the exponent. So I multiply this 2 by the x plus 1. So this would be 2 to the power of, and 2 times x plus 1 would be 2x plus 2. Remember, you go 2 times x is 2x, and 2 times the 1 is 2. Same thing on the right side. Now if these powers are the same, are equal, and that's what that sign says right there, and the bases are the same, they're both 2's, the only way they can be equal is if this exponent, 2x plus 2, is equal to x minus 1. I couldn't have the bases the same and those powers equal and have the two exponents not being equal. It wouldn't be possible. It would be like saying 2 cubed is equal to 2 to the 9th. Okay? It's not possible. The exponents would have to be the same if the bases are the same and the whole powers are equal. And so we don't actually, a lot of students think we divide out the 2's, the bases. We're not. We're saying that if these powers are the same, or equal, then this exponent is equal to this exponent. So we kind of drop the bases. That's probably the best way to describe it, sort of non-mathematically. But we're just saying that if these powers are equal, then the exponents must be equal, and that's how we find what x is. So I rearrange. I'll subtract x from both sides to get the x's alone on the left, and I would subtract 2 from both sides to get the numbers alone on the right. And so rearrange, we have 2x minus the x equals this negative 1 minus this 2. And so this simplifies to just x on the left, and negative 1 minus 2, of course, is negative 3. Now I could verify that this is the solution, the negative 3. And so my check would look like this. I'm going to substitute negative 3 in place of x on the left. So remember, LS stands for left side. So I'm putting negative 3 here in place of x. I'm going to verify that this works out to the same as what's on the right side. Now in the exponent, negative 3 plus 1, of course, that's negative 2. So I have 4 to the negative 2. Remember, that's the same as 1 over 4 squared, which is 1 over 16. So the left side value is 1 over 16. I'll do the same thing on the right. The right side, we're putting, again, negative 3 in place of x here. So negative 3 minus 1, of course, is negative 4. So I have 2 to the negative 4. So that's the same as 1 over 2 to the 4th. And, of course, 2 to the 4th is 16. So I get the same thing. The left side and right side both work out the same thing. So that checks. That assures us that the answer is correct. Similar idea in B to solve, where I want to write both sides as powers of the same base. So I have 9 and 27, and the common base would be 3. I can write 9 as 3 squared and 27 as 3 cubed. So I'm writing with powers of 3 on both sides. So now again, I have a power of a power, so I multiply the exponents. 2 times 3x is 6x, and 2 times the 1 is 2, and then just 3 times x is 3x on the right side. Now again, I have powers of the same base, so in order for these to be able to be equal, this exponent 6x plus 2 must equal this exponent 3x. And so I drop the bases and say this exponent must equal this exponent, and I solve for x. So I would rearrange 6x minus 3x, and of course subtracting 2 from both sides, I'd be left with negative 2 on the right. So we get 3x equals negative 2, and then we divide out the 3 to solve for x. So x would be negative 2/3. And that's the end of the lesson.